Tell us a little about the most magnificent curiosities of the universe. Well, I've been thinking a lot, actually, about the beginning of it all. The very beginning, the moment before moments existed. You see, the Big Bang, it's not just a bang, not like an explosion in space. It's the birth of space itself and time. Time, too. There wasn't anything before it. No space to expand into, no time ticking away, just nothing. Or maybe something we can't really describe. It's a strange thing, isn't it? And then suddenly there's this moment, this singular point, infinitely hot, dense beyond comprehension, and it expands. It doesn't explode outward into a pre-existing space. It creates the space as it expands. That's what's so hard to picture. We think of explosions happening in space. But this was space being born, and time begins to flow. Before that, there's no before. There's no earlier. The word before just loses meaning. This expansion incredibly fast, we call it inflation. A fraction of a second, and the universe inflates exponentially from a subatomic scale to something enormous. It's smooth. That's the bizarre thing. Smooth and uniform almost perfectly. So with tiny fluctuations, ripples really frozen into it. Quantum fluctuations stretched across cosmic scales, and those little imperfections, they become everything. Galaxies, stars, planets to us. But I always stop and ask what caused it. Why did that singularity, why did it exist in the first place? Was it inevitable? Was it a fluctuation in some kind of prejay? These are real ideas. Well, speculative, yes, but serious ones. Some physicists talk about quantum tunneling from nothing, a state with zero energy that suddenly pops into existence. Because, strangely enough, the total energy of the universe could be zero positive energy in the form of matter balanced by negative gravitational energy. So maybe nothing really cost anything to create. Maybe the universe is a free lunch, strange as that sounds, and that's just the start. Because once space-time is born, the laws of physics emerge. They're not imposed on it from outside. They unfold with it. The fundamental forces, gravity, electromagnetism, the nuclear forces, they differentiate as the universe cools. Symmetries break. Particles acquire mass. The universe becomes structured, governed, and yet it's still expanding. Even now, even as we speak, it's stretching faster and faster. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. It costs you nothing, but it helps me enormously in this journey of sharing knowledge. So, let's continue. Driven by something we don't fully understand. Dark energy. Maybe a name, really, more than an explanation. But that moment, that singularity, or what we call the singularity, we can't really see it. The physics breaks down there. Our equations, they just don't work at that point. So we extrapolate mathematically backwards in time, and everything seems to converge. But whether it's a true beginning or just a veil hiding a deeper reality that's still unknown, still that first flicker, that emergence of time itself, that's the beginning of every story ever told. Everything we know, everything we are, traces back to that unimaginable moment when the universe became, when it decided somehow to begin. And then there's the vacuum, the quantum vacuum. People think of it as empty space, but it's not empty. Not really. It's teeming, absolutely teeming with energy, with particles and antiparticles that appear and disappear constantly, just flickering in and out of existence. It's a kind of seething, fluctuating field, not visible, but it's there, always there. And it's not just some background noise. It's fundamental. It's the bedrock, if you like, of everything. In quantum field theory, every point in space, it's like a little harmonic oscillator. It can't just sit still at zero energy because of the uncertainty principle. So even the lowest energy state, the so-called ground state, it has energy. That's the vacuum energy. And it's not uniform. Well, it's statistically uniform, but with fluctuations, tiny ones. And these fluctuations, they're not just theoretical curiosities, they have consequences, real consequences. Without them, there wouldn't be structure. There wouldn't be galaxies or planets or stars or anything. It's those fluctuations, those tiny random ripples in the vacuum that were stretched during inflation, stretched across the entire universe. They became the seeds, the beginnings of all the large-scale structure we see today. So, in a sense, the vacuum, the quantum vacuum, wrote the first draft of the cosmic story. The gravitational pull of those slightly denser patches in the vacuum over billions of years. It drew in matter-formed galaxies and eventually us. It's almost poetic, but it gets stranger. Because some theories suggest that the universe itself, that it emerged from a quantum fluctuation in this vacuum. That the whole of existence could be a spontaneous random event. That this vacuum isn't just passive. That it can, under the right conditions, give birth to space, time, and energy. You start with a quantum vacuum, just this strange energetic nothingness. And suddenly there's something, a bubble of space-time, a universe. Of course, that raises questions, a lot of questions, like what governs the vacuum? What determines its properties? Is it unique, or are there many different kinds of vacuums, each with its own physical laws? That's where things start to blend into the multiverse idea, but we're not quite there yet. What's remarkable is that we've actually observed effects of this vacuum. Casimir effect, for instance, two metal plates placed extremely close together in a vacuum. They attract each other not because of any external force, but because the vacuum itself behaves differently between the plates than outside them. The vacuum exerts a pressure. And that's just one example. Virtual particles affect real physics. They shift energy levels in atoms. They contribute to the structure of matter. They're invisible but measurable. So this idea of the vacuum as nothing, it's just not accurate. It's more like a field of potential, a restless ocean of possibilities. And it may be the very source from which our reality first emerged. Not a void, but a kind of womb, a cradle, a starting point filled with everything and yet nothing at all. It's hard to say how many there are. How many universes? Because the idea that this is the only one, the only reality that's starting to seem, well, not wrong exactly, but incomplete. The more we look into the mathematics, into the implications of inflation and quantum mechanics and string theory, the more it looks like there might be other universes, parallel realities, the multiverse. And it's not science fiction anymore. Not really. It's one of those things where the equations start leading you somewhere strange. During inflation, for instance, the rapid expansion of space, it might not stop everywhere at the same time. Some regions they keep inflating, while others bubble off, stop inflating, and form, what we'd call universes. Entire disconnected regions of space, like little bubbles in a foam. Each one with its own laws, its own constants, its own version of physics. Ours is just one of them. One bubble in an endless, ever-growing sea. Now that's eternal inflation. That's one way you get a multiverse. But then there are others. There's the many worlds interpretation of quantum mechanics where every quantum event, every decision, every possibility doesn't collapse into one outcome. It branches. It all happens. Every path taken, every coin flip, every uncertain moment, it all splits the universe into new versions of itself. So in that picture, there are versions of you and me having different conversations, making different choices endlessly. And those worlds aren't out there far away. They're right here, interwoven, invisible, unreachable, but maybe real. It's strange, though, isn't it? That all of it comes from equations, from math. We don't have direct evidence of these other worlds. We can't see them, can't visit them. But the theories that predict them, they also predict other things. Things we can test, like the distribution of temperature in the cosmic microwave background, or the way particles behave in colliders. And if those predictions match, if they hold, then maybe the rest of the theory, the part we can't test, has to be taken seriously too. Some even suggest that black holes, those strange objects where space and time seem to end, might be gateways, not wormholes exactly, not like science fiction. But maybe when something falls in, when information goes in, it doesn't just vanish. Maybe it seeds a new universe on the other side. A daughter universe connected only by gravity, by history. We don't know, we really don't. And then there's the Anthropic principle. The idea that in a multiverse, most of the universes are sterile, empty, dead. But in this one, everything happens to be just right. The constants, the particles, the forces perfectly tuned so that galaxies can form, stars can burn, chemistry can happen, life can emerge. So we find ourselves here not because it's likely, but because it's the only place we could be. We observe this universe because it's the one where observers exist. Still there's something unsettling about it. The thought that we might be just one of countless others. That reality itself is bigger, much bigger. That this universe isn't everything. It's just one page in an infinite book. If you go far enough back, if you go back before us, before the sun, before even the planets began to take shape, all you'd see is gas. Just enormous clouds of hydrogen and helium drifting, collapsing, pulled inwards by gravity. These clouds, vast, cold, mostly featureless, were the beginning. And over time, over millions of years, they began to clump, to condense. Little knots of matter growing denser, hotter, until suddenly there's fusion, there's light. The first stars igniting, and that changes everything, because before those first stars, the universe was dark. Not metaphorically, literally dark. No light had ever been emitted. But now there are points of light scattered across the black, and with them comes structure. You get clusters, then galaxies. Hundreds of billions of them rotating, merging, evolving, some spiral, some elliptical, others irregular, chaotic. And it's all gravity. Just gravity shaping everything. But slowly, so slowly that you'd never notice it happening in real time. Stars form in waves, generations, each one living out a lifespan that depends on its mass. The big ones, the really massive stars, they burn fast, burn bright, and die young. A few million years, that's all they get. And the smaller ones, like red dwarfs, they live well. They could live for trillions of years. But in those early days, it was mostly the giants. Massive stars forming in dense regions, fusing hydrogen into helium, then into carbon, oxygen, heavier and heavier elements until they can't anymore. And when they can't, when iron starts to build up in the core, everything collapses instantly. The outer layers fall inward, hit the core, bounce outwards, and explode. That's a supernova. A single star outshining an entire galaxy just for a moment. And that moment, that explosion, it's where most of the elements come from. The gold, the calcium in your bones, the iron in your blood. All of it forged in dying stars. It's not poetry. It's just the way things are. But these stars, they didn't form alone. They came together orbiting a common center, pulled by their own gravity into vast structures, galaxies. And over billions of years, galaxies merged. They collided. Their stars didn't crash into each other, not often because the distances are so vast. But the gas clouds did, and those collisions triggered new waves of star formation, bursts of activity, lighting up the darkness. Even now, the Milky Way, it's still growing, still devouring smaller galaxies. And in the center of almost every one of these spirals, there's something strange, something massive. A black hole, millions, sometimes billions of times the mass of the sun. But that's another story. Still, this is how it begins. Not with us, not with Earth, but with the stars. Born from collapsing clouds of gas shaped by gravity, burning for millions or billions of years and dying spectacularly. And in their deaths, they give us the ingredients for everything. For rocks, for oceans, for life. They were the alchemists of the cosmos. There's something about them, something terrifying and beautiful at the same time. Black holes, these things, they're not just stars that collapsed. They're the end points of space and time. When a massive star reaches the end of its life, sometimes there's nothing left to resist gravity. The core collapses in on itself beyond the point of no return. And what you're left with is, well, it's a region. A place where gravity is so strong, so overwhelming that nothing, not light, not time, not even information can escape that boundary. We call it the event horizon. But here's where it gets strange. From the outside, from a distance, you'd never see anything cross it. An object falling in, it would appear to freeze just above the surface, slowing down, red shifting, fading away. But from the falling object's point of view, it's different. It falls right through. No drama, no resistance. And inside, no one really knows. The equations break down. Time and space swap roles. The future becomes a direction inwards, and everything, absolutely everything, is drawn to the center, to the singularity, a point where the density becomes infinite, Or maybe not a point at all, maybe just the limit of our understanding. Now, the real problem is information, because in physics, information is supposed to be preserved always. That's what quantum mechanics demands. But when something falls into a black hole, a book, a planet, a person, what happens to the information about that object? All the particles, their arrangement, their state. Is it lost? Burned away as the whole evaporates, because they do evaporate. Hawking showed that not quickly, but over time they emit radiation. Slowly, imperceptibly they shrink, and eventually they disappear. So then, where did it all go? That's the paradox. If the black hole vanishes and the information is truly lost, then quantum theory breaks. But if the information somehow gets out, where is it? In the radiation? That seems impossible. But maybe not. Some think the information is encoded on the event horizon itself, like a hologram, a surface storing all the data of the interior. That's the holographic principle, a whole universe inside encoded on the edge. And there's another idea: firewalls. The notion that instead of passing smoothly through the horizon, an infalling object hits a wall of energy vaporized instantly, that would preserve the information. But it would also mean something's wrong with our current understanding of general relativity. Because general relativity says crossing the horizon should feel like nothing, just falling, no drama. But if there's a firewall, then something dramatic happens. Very dramatic. So we're stuck. Two of the most successful theories ever devised, quantum mechanics and general relativity, are in conflict. And the battleground is the black hole. It's like a knot in our understanding. A place where the laws we rely on just stop agreeing with each other. So we're left with a puzzle, a mystery that's not just academic, because whatever the answer is, it might point the way to something deeper, something beyond both, a new theory, a deeper truth, one that finally unites everything. There's a moment, a very specific moment, when a star dies, and it doesn't just fade away quietly. It detonates, explodes, a supernova. These aren't just fireworks. They're cataclysmic, violent, unimaginably powerful. A single one of these explosions can outshine an entire galaxy for a brief time. And what they leave behind is just as important as the blast itself. So you've got a massive star burning elements in its core, hydrogen to helium, helium to carbon, carbon to neon, and so on, building up layers like an onion. But when it hits iron, when the core becomes mostly iron, that's it. That's the dead end. Iron doesn't yield energy when it fuses. It costs energy, and so fusion stops. The outward pressure that had been holding gravity at bay, it vanishes, and the core collapses instantly. In a fraction of a second, the star's core shrinks. Protons and electrons crushed into neutrons. And then boom, the outer layers rebound, driven outwards by a shock wave. Neutrinos flood out, trillions of them, passing through everything. The entire outer envelope of the star is blasted into space. That's the supernova. And it's in that fireball, that chaos, where the heavy elements are born. Gold, silver, uranium, everything heavier than iron, forged in the extreme temperatures and pressures of the explosion. It's astonishing. The iron in your blood, the iodine in your thyroid, the calcium in your bones, it all came from stars that exploded long before the Earth even existed. They gave their lives, in a sense, for matter to be recycled, reused. Nothing is wasted, not out there. And there are types. Type 1, for instance, doesn't come from a single massive star. It comes from a white dwarf in a binary system. The dwarf pulls material from its companion star, and when it reaches a critical mass, it detonates. That's different. That's not a collapse, it's a thermonuclear runaway. But still, it enriches space with elements. It contributes. It completes the cycle. These explosions don't just create matter. They stir things up. They send shock waves through space, compressing clouds of gas, triggering the birth of new stars. Supernova remnants, the expanding shells of gas and dust, glow in radio, X-ray, visible light. They're beautiful and eerie, like fingerprints left by the dead. And sometimes what's left behind is even stranger. A neutron star, incredibly dense, a spoonful of it would weigh billions of tons. Or if the core was massive enough, a black hole, a scar on space-IME itself. But always these events mean change, renewal, a kind of cosmic recycling. One generation of stars dies, and from their ashes another begins. The universe doesn't waste anything. The atoms in us, every one of them were once inside a star, a dying star, a star that exploded. And that explosion, that moment of death, gave rise to everything we know, everything we are. There's this moment, a strange, improbable moment where the dust, the gas, the debris from ancient stars, it all comes together, collides, spins, clumps, and out of that chaos a planet forms. Not just any planet, this one, this pale blue dot, Earth. And that in itself is remarkable. But what came after is even stranger, because somehow on this little world, the universe learned to think to observe itself. But let's go back the early Earth. It wasn't peaceful. It was violent, molten, battered by impacts. No oceans, no atmosphere as we know it. And yet even then conditions were just right. Just right for chemistry to begin. Complex molecules forming in shallow seas, or maybe around hydrothermal vents, maybe both. No one really knows. But somewhere, somehow, non-living matter turned into life, that transition. It's still one of the great mysteries. Not just how it happened, but why here? Why now? The solar system had other planets, Mars, Venus. They could have been contenders, but something about Earth was special. It wasn't too hot like Venus. It didn't lose its atmosphere like Mars. It had water. It had stability. It had time. Billions of years for life to grow more complex, to adapt, to evolve. And that's the next thing, because life didn't just appear and stay the same. It changed slowly. At first, single cells adapting to their environment. Then much later, multicellular organisms, eyes, limbs, nervous systems, and eventually consciousness, thought, language, curiosity. But what's striking, what's really strange, is how unlikely it all seems. When you look at the odds, how precise the conditions have to be, it feels like a miracle. But it's not magic. It's physics. It's chemistry. It's the laws of nature playing out with extraordinary consequences. And all of that complexity arises from simplicity, from hydrogen, helium, carbon, from atoms forged in stars and arranged over time into molecules, into cells, into us. So the singularity of life, its rarity, its beauty, it's not in the ingredients, it's in the arrangement, the structure, the process. Still, we wonder, is it unique? Is this the only place where it happened? Maybe not. Maybe life is common. Maybe given the right conditions, it emerges everywhere. Or maybe we are rare. Maybe we are alone, a single spark in a vast dark ocean. But whether life is common or rare, it is here astonishing because it didn't have to be. This planet could have remained sterile, just rock and ocean and sky. But instead, it blossomed, and through life the universe became aware of itself. We look out now from this tiny world and we ask questions. We build telescopes. We run simulations. We wonder where we came from, where we're going. But at the center of it all is this improbable world. And on it, a phenomenon we still don't fully understand. Life, consciousness, meaning. There's something about it, something that feels almost unnoticed, taken for granted. And yet it's everything. The moon, that distant, quiet presence in the sky. But it's more than just a companion. It's a stabilizer, a guardian. Without it, things could have been very different. The Earth doesn't just spin. It tilts. It leans about 23.5 degrees. And that tilt, that's what gives us seasons, climate patterns, long-term stability. But here's the thing. The moon helps keep that tilt steady. Without it, the Earth would wobble chaotically, shifting back and forth over millions of years. Imagine a planet with its axis flipping unpredictably. Poles becoming equators. Climate swinging from ice to fire. That's what the moon prevents. It's not just gravity, it's resonance, the size of the moon relative to Earth. It's unusually large, almost a double planet. And that size means it has enough mass, enough pull to keep Earth's orientation stable. A kind of cosmic anchor. And that matters. It matters because life doesn't thrive in chaos. It needs constancy, predictability, the long, slow rhythm of the seasons, the quiet pulse of planetary time. And then there are the tides, that gentle rise and fall of the oceans. It's not just poetic, it's practical. The moon's gravity pulls at Earth's oceans, dragging them slightly off-center, creating bulges. As the Earth spins, those bulges move, and that motion stirs the seas, mixes nutrients, drives currents. It's like a planetary breath. And in the shallows where those tides reach furthest, life may have found its first foothold. Pools that filled and dried again and again, giving molecules a chance to bond, to fold, to replicate. Some theories even suggest that early life, complex life, might owe its existence to the moon's pull. That the tidal zones, those shifting borders between land and sea, were laboratories, places of chaos, yes, but also of opportunity. Repeated cycles of exposure and submersion, wet and dry, energy flowing in and out. And over time, over unimaginable time, life became more complex. Cells cooperated, structures emerged, multicellularity, movement, eyes. The moon may also have helped in another way, slowing the Earth's spin. Long ago, a day on Earth lasted just a few hours. The planet spun like a top, but the moon's gravitational pull created friction, tidal breaking. Gradually, the days lengthened. The rhythm of life slowed down, and that too may have helped. Gave life time to evolve, to adapt, to change. And beyond all that, there's the moon as a clock, the earliest calendars. They watched the moon, counted its phases, farmers planted by it, priests worshipped it, poets wrote about it. It gave us time long before we understood what time really was. So this silent partner, this sphere of rock hanging in our sky, it's more than scenery. It's woven into our history, into our biology, into everything we are. And yet it's just there quiet, watching, pulling, guiding. From the very beginning, it's strange. Really strange to think that for most of human history, we didn't know they existed. Planets orbiting other stars, exoplanets. Now we know of thousands, confirmed, cataloged, studied, and probably billions more. Everywhere we look, there are stars and around them worlds. Some small, rocky, some vast and gaseous, some scorched, some frozen, and maybe, just maybe, some like ours. But the first ones, the very first exoplanets we found, they weren't like Earth. Not even close. Hot Jupiters, we called them. Giant planets orbiting so close to their stars that a year lasts only a few days. We didn't expect that. We thought our solar system was typical, but it's not. Or at least not in the way we assumed. These early discoveries forced us to rethink everything. We detect them in clever ways, not by seeing the planets directly, because that's hard. The star's light overwhelms the planet's faint glow, but we watch for wobbles. The tiny pull a planet exerts on its star as it orbits. Or we look for dips in brightness when a planet crosses in front of the star, blocking a fraction of the light. Transit photometry. It's like watching a fly pass in front of a spotlight from thousands of kilometers away. And from that tiny signal, we can learn so much. The size of the planet, its orbit, sometimes even the composition of its atmosphere. We've detected water vapor, methane, carbon dioxide in clouds swirling around alien skies. We've seen storms on distant worlds, winds faster than sound, temperatures that melt metal. But we keep looking for something else, something more familiar. The habitable zone, that narrow band around a star where water could exist as a liquid. Not too hot, not too cold, just right. The Goldilocks zone. That's where we hope to find life. Maybe not like ours. Maybe stranger, simpler, but alive, breathing, changing, evolving. And some of these planets, some of them might fit. TRAPPIST 1, for example. A tiny star with 7 rocky planets, 3 in the habitable zone. They're close, not in distance, but in potential. And that's exciting. We're also looking for Earth twins, not just rocky planets, but the right size, right atmosphere, orbiting stable stars. And with missions like Kepler, TESS, and soon the James Webb and beyond, we're getting closer. Closer to finding a world that's not just habitable, but inhabited. A world with biosignatures, gases in the atmosphere that shouldn't be there unless something is alive. Oxygen, methane, maybe even chlorophyll, who knows? And then there's the thought, the quiet, unsettling thought that we might not be alone, that life isn't unique to Earth, that the universe might be full of voices we haven't heard yet. Or maybe it's silent, vast, and empty, and we're the exception. Either way, the discovery changes everything. Because in finding another world, We're really finding out who we are. There's something about time that feels obvious. But when you think about it, really think about it, it slips away. We feel it moving, flowing forward, always forward. But why? Why does time have a direction? Why can't we move backwards? Why do we remember the past but not the future? It's not built into the laws of physics, not really. Most of the equations work the same forward or backward. Time symmetry, they call it. But our experience, our reality is not symmetrical at all. And the answer, or at least part of it, seems to lie in entropy. Entropy is, well, it's a measure of disorder. The number of ways a system can be arranged. The more disorder, the higher the entropy. And the second law of thermodynamics says entropy always increases, always. That's the arrow of time. That's what gives us a before and an after. So if you take an egg and smash it, it's easy. The shell shatters, the yolk spreads out, everything becomes more disordered. But try doing it the other way around. Try unbreaking the egg. It doesn't happen. Not because the physics won't allow it, but because the number of ways to be broken is vastly astronomically higher than the number of ways to be whole. So entropy increases and time moves forward. But that raises another question. If time flows from low entropy to high entropy, then why was the past so ordered? Why was the universe born in a state of such low entropy? The early universe hot, dense, uniform. But uniformity, that's low entropy, and that's odd because a clumpy universe with stars and black holes and galaxies, that's higher entropy. So the question is, why did it begin that way? Roger Penrose proposed something called the whale curvature hypothesis. The idea that the gravitational field of the early universe was somehow constrained, that there was a kind of order, a symmetry built into the fabric of space itself, and as the universe expanded, that symmetry broke down. Gravity took over, structure formed, entropy increased, but we don't know why. We don't know why, though the boundary condition of the Big Bang was so special, so asymmetric. It's one of the deepest mysteries in cosmology. Because if you could explain that, if you could explain why the universe started in a low entropy state, you'd understand why time flows the way it does. You'd understand why there's memory, why there's causality, why we age. Some theories suggest that time might run backwards in another part of the universe, that the arrow we feel is local, not universal, that somewhere else there could be beings watching their past as we watch our future. It sounds impossible, but mathematically it isn't ruled out. Still we live in a universe where entropy increases, where yesterday leads to today and today to tomorrow. And though we don't know why it began like this, we know this. The direction of time, the arrow we ride, it's written not in the equations, but in the history of the universe itself. It's one of those things we don't often think about, not directly. The constants, the numbers that define everything, the speed of light, 299, 792, 458 m per s. Planck's constant, the gravitational constant, the mass of the electron. These numbers, they just are fixed, immutable. But why those values? Why not different ones? What chose them? Or rather, what determined them? That's the question. That's the mystery. Because if you change them just a little, just slightly, the whole universe, it changes completely. Stars might not form, or they'd burn too quickly. Chemistry might not happen. Atoms could become unstable or too stable. The forces wouldn't balance. Life as we know it wouldn't stand a chance. It's like walking a tightrope, and the universe walks it perfectly balanced between chaos and emptiness. Some people talk about fine-tuning, that the universe seems almost suspiciously tailored for life. But is that real, or is it just selection bias? Of course, the constants seem perfect to us. We're here to